About 700 light-years from Earth, there is a gigantic thing in space that seems to be watching us. Scientists call it the Helix Nebula, but many people know it by another name, the Eye of God, when telescopes pointed there for the first time. What they saw changed everything we knew about how stars die. It is not a violent explosion like many imagine. It is something much slower, more beautiful, and in a way more frightening. A star similar to our Sun released its outer layers into space, creating this glowing circle that looks like a cosmic eye staring directly at us. Get ready to fall asleep while listening to this video and travel through this landscape of ancient light. Could this giant eye in the sky be trying to tell us something about the future of our own sun? Subscribe to the channel. Leave your like and comment where in the world you are watching from. Get comfortable and relax. Let us begin. Have you ever looked up at the night sky and seen a shape that reminded you of something familiar? That is exactly what happened with the Helix Nebula, leading to its famous nickname, the Eye of God. But the real story behind its discovery and naming is a fascinating journey through the history of astronomy. The Helix Nebula was not discovered in one single moment of brilliance, but was gradually identified and catalogued over many years by several astronomers who were piecing together the mysteries of the cosmos. In the early 19th century, around 1824, Carl Ludwig Harding is often credited with its discovery, but it is important to note that other stargazers might have observed it earlier without fully understanding what they were seeing. At that time, telescopes were not as powerful as they are today, and the nebula's faint, diffuse appearance made it easy to mistake for a comet or a distant star cluster. This initial confusion was common in an era when astronomers were still mapping the heavens and distinguishing between different types of celestial objects. The big step forward came when the Helix Nebula was entered into the new general catalogue, where it received the designation NGC7293, solidifying its place in astronomical records and making it easier for future generations to study and reference. This catalogue was a monumental effort to organise and document deep sky objects, and it played a crucial role in standardising how we talk about and locate things in space. The popular nickname, the Eye of God, emerged much later, largely thanks to high-resolution images captured by advanced telescopes like the Hubble Space Telescope, which revealed intricate details and a striking resemblance to a human eye. These images, circulated widely in the media and online, captured the public's imagination and turned the nebula into an icon overnight. This phenomenon is not unique to the Helix Nebula. It is an example of pareidolia, which is the human tendency to perceive familiar patterns, like faces or shapes, in random or ambiguous stimuli. We see it everywhere, from seeing animals in clouds to spotting a man in the moon. And it speaks to how our brains are wired to find meaning and structure in the world around us. In the case of the Helix Nebula, this psychological quirk transformed a scientific subject into a cultural symbol, blending astronomy with popular culture in a way that resonates with people on an emotional level. The evolution of its name reflects broader changes in how we engage with science as technology improved, allowing for clearer and more detailed views of space. Our interpretations became more nuanced, yet we still clung to poetic and imaginative descriptions. The story of the Helix Nebula's discovery also highlights the collaborative nature of astronomy, where contributions from multiple observers over time build a more complete picture. For instance, before Harding, other astronomers might have noted the nebula in their logs, but it was his work that brought it into the spotlight, thanks in part to the growing interest in nebulous objects during that period. The new general catalogue itself was a product of collective effort, compiled by John Lewis Emile Dreyer based on observations from many sources, and it became a foundational tool for both professional and amateur astronomers. As the 19th century progressed, improvements in telescope technology and photographic techniques allowed for better observations, slowly revealing that the helix was not a star cluster but a cloud of gas and dust, though its true nature as a planetary nebula would be understood later. The term planetary nebula is actually a misnomer coined by William Herschel, who thought these objects resembled planets. But we now know they are the remnants of dying stars, which adds another layer to the helix's story. The nickname Eye of God gained traction in the late 20th and early 21st centuries, as space agencies released stunning images that went viral, making the nebula a favourite among space enthusiasts and artists alike. This cultural adoption has had a positive impact, sparking interest in astronomy and inspiring people to learn more about the universe. Even if the name is not scientifically accurate, it shows how science communication can benefit from relatable metaphors, making complex concepts accessible to a wider audience. However, it also raises questions about the balance between scientific accuracy and public perception, as nicknames can sometimes lead to misunderstandings about what these objects truly are. Despite that, the Helix Nebula's case demonstrates how cultural narratives can enhance our connection to science, turning abstract data into stories that we can share and discuss. The interplay between discovery and nomenclature is a recurring theme in astronomy. As we find new objects, we name them based on our current knowledge and cultural context, and those names can evolve over time. For the Helix Nebula, its official designation, NGC 7293, is used in scientific papers, while the Eye of God dominates popular discourse, creating a dual identity that serves different purposes. This duality is not uncommon. Many cosmic objects have both technical names and popular nicknames that reflect different aspects of human curiosity. Exploring the history of the Helix Nebula's discovery also involves acknowledging the limitations and achievements of past astronomers, who worked with rudimentary tools yet laid the groundwork for modern astrophysics. Their meticulous observations and record-keeping allowed later generations to build upon their work, leading to breakthroughs in understanding stellar evolution and the life cycles of stars. The Helix Nebula, as one of the closest planetary nebulae to Earth, has become a key subject for study, helping astronomers learn about the processes that shape such objects and, by extension, the fate of our own sun. But before all that science could happen, it had to be found and named. And that process was shaped by human factors like curiosity, persistence, and the urge to find meaning in the stars. The role of pareidolia in astronomy is not just a trivial side note. It has influenced how we chart and remember the sky. From ancient constellations to modern nicknames, it reminds us that science is a human endeavour, infused with our perceptions and cultural backgrounds. The Helix Nebula's journey from a fuzzy patch in the telescope to the Eye of God mirrors the evolution of astronomy from a visual craft to a data-driven science. Yet it also shows that our innate desire to see ourselves in the universe remains strong. As we continue to explore space with ever more sophisticated instruments, we will undoubtedly discover more objects that capture our imagination and receive names that reflect our times. The story of the Helix Nebula encourages us to appreciate both the scientific and the human sides of discovery, where facts and imagination coexist, enriching our understanding of the cosmos. In the end, whether we call it NGC 7293 or the Eye of God, this nebula continues to inspire wonder and curiosity, proving that the way we name things can be as meaningful as the things themselves. after learning about its discovery and the story behind its name. The next natural step is to locate the Helix Nebula in the vast expanse of the night sky, a journey that begins with understanding its cosmic address. You will find it nestled within the constellation Aquarius, which is not particularly famous for bright stars, making this region of the heavens a bit challenging for casual stargazers to navigate. The nebula sits approximately 650 light-years away from Earth, which places it among the closest planetary nebulae to our planet, offering a unique and relatively accessible window into the death throes of a star. To actually spot this celestial eye, you will need a telescope with a moderate to large aperture, and even then, success hinges on finding very dark skies, far from the pervasive glow of city lights that washes out faint deep sky objects. The process of finding it involves more than just randomly pointing a telescope. It requires some familiarity with celestial coordinates and star patterns, often using a technique called star hopping. This method involves starting from a known dot, bright star, and making small, careful jumps to fainter stars until you arrive at your target. For the Helix Nebula, a good starting point is the star Saddle-Sud, the brightest star in Aquarius, and from there, you can navigate using a detailed star chart or a digital planetarium app on your phone. The constellation Aquarius itself is best viewed during the late summer and autumn months in the Northern Hemisphere, when it climbs highest in the sky, though observers in the Southern Hemisphere can also see it, albeit lower on the horizon. Why is the helix so faint and elusive? Its apparent brightness is spread over a relatively large area in the sky, about half the size of the full moon, which means its light is diffuse and doesn't concentrate into a sharp point, making it harder to detect against the background. When you finally manage to see it through the eyepiece, don't expect the vibrant colours seen in famous Hubble images. To the human eye, it will likely appear as a faint, greyish, smoky ring or a patch of light, because our retinas aren't sensitive enough to perceive colour in such low light conditions. This visual experience is still profoundly moving, knowing you are gazing at the aftermath of a star's death. The light you are seeing has been travelling through space for 650 years, meaning the photons entering your telescope began their journey around the time of the Renaissance on Earth. A tangible reminder that astronomy is a form of time travel. This distance also means that we are seeing the nebula as it was centuries ago, not as it is in the present. And any changes happening there now won't be visible to us for another 650 years. The concept of light years is crucial here. It is not just a measure of distance, but of time, encapsulating the history of the object we observe. For amateur astronomers, finding the helix is a rewarding challenge that connects them to a long tradition of celestial navigation, akin to how ancient sailors used the stars to cross oceans. Today, we have tools like equatorial mounts and go-to telescopes that can automatically slew to the correct coordinates. But learning to find it manually deepens your understanding of the sky's layout. The nebula's coordinates are right ascension around 22 hours 29 minutes and declination about -20 degrees 50 minutes. But in practice, most people use visual cues from surrounding stars. Another helpful marker is the asterism known as the water jar in Aquarius, a small pattern of stars that can serve as a stepping stone under truly dark skies. With no moon and excellent transparency, some experienced observers with large telescopes report seeing hints of the nebula's structure, like the darker central region that gives it the eye-like appearance. However, for most, it remains a subtle, ethereal glow. The journey to observe the helix is also a lesson in patience and preparation. You need to allow your eyes to adapt to the darkness for at least 20 minutes. Use averted vision by looking slightly away from the object to engage more light-sensitive rod cells in your retina, and possibly employ filters that block light pollution and enhance the contrast of emission nebulae. An oxygen-3 filter, for example, can dramatically improve the view by isolating the light from doubly ionized oxygen atoms in the nebula. Beyond visual observation, astrophotographers capture its beauty by taking long exposure images, sometimes totaling many hours over several nights, to accumulate enough light to reveal the intricate details and colours. This technical aspect highlights how modern astronomy blends art and science. The proximity of the Helix Nebula allows professional astronomers to study it in exceptional detail, using instruments across the electromagnetic spectrum to unravel its physics. Its relative closeness means that its angular size is large enough to resolve fine structures, like the cometary knots and the faint outer halo, which would be impossible for more distant nebulae. This detailed study helps scientists understand the processes of mass loss and ionization in dying stars, which in turn informs models of stellar evolution. When you find the helix, you are not just looking at a static picture, you are witnessing a dynamic, expanding cloud of gas. Spectroscopic measurements show that the nebula is growing larger at speeds of tens of kilometers per second, but on human timescales, it appears unchanging. The act of locating it also immerses you in the scale of the universe. The 650 light-year distance is immense, yet it is a mere stone's throw in galactic terms. Our own Milky Way galaxy is about 100,000 light-years across, so the helix is a relatively local object. This perspective can be both awe-inspiring and humbling for those without access to a telescope. Many observatories offer public viewing nights or live-streamed events where you can see the helix through professional instruments. Online resources like satellite imagery and virtual planetariums also provide ways to explore it digitally. The cultural significance of the Eye of God adds an emotional layer to this hunt. Knowing its nickname and the stories behind it can make the observation feel more personal and meaningful. However, the scientific importance remains paramount. By studying objects like the helix, we learn about the fate of our own sun, which will one day undergo a similar transformation. The journey to find the Helix Nebula is thus a multifaceted experience, combining technical skill, historical context, and a deep connection to the cosmos. It reminds us that the night sky is a vast, accessible library of stories waiting to be read, and each object we find adds a new chapter to our understanding. So, if you are eager to start this adventure, begin by familiarizing yourself with Aquarius on a clear night. Use whatever equipment you have, and remember that every successful observation is a small victory in the lifelong journey of astronomical discovery. The helix may be challenging to find, but the effort is richly rewarded by the profound sense of wonder it inspires, linking you directly to the ongoing narrative of the universe. Now that you have managed to locate that faint, smoky ring in Aquarius and felt that sense of wonder, it is time to unravel what this beautiful object actually represents. Because the term planetary nebula is one of the most misleading names in all of astronomy. It has nothing to do with planets. The name is a historical accident from the late 18th century when the astronomer William Herschel, using his telescopes, observed these round, fuzzy objects and thought they resembled the distant gas giants like Uranus, which he had discovered. He coined the term because through the eyepiece, they appeared as small, greenish disks, similar to how a planet might look. But we now know they are something entirely different and far more dramatic. The Helix Nebula is a spectacular example of a planetary nebula, which is actually the final, brilliant act in the life of a star similar in mass to our own Sun. This process begins when a star exhausts the hydrogen fuel in its core that has been powering it for billions of years through nuclear fusion. With the fusion engine sputtering, the balance of forces within the star is disrupted. The outward pressure from fusion reactions can no longer counter the immense inward pull of gravity. This causes the core to contract and heat up significantly, while the outer layers of the star expand outward dramatically, cooling down and transforming the star into a red giant. In the case of a star like the one that created the Helix, this red giant phase is unstable and relatively short-lived. The star begins to pulsate, violently shedding its outer layers into space in a series of energetic outbursts over thousands of years. This ejected material forms a vast, expanding shell of gas and dust that we see as the nebula itself. Meanwhile, the exposed hot core of the star, no longer supported by fusion, collapses under its own gravity into an incredibly dense object called a white dwarf. This white dwarf is composed mostly of carbon and oxygen, the ashes of the star's earlier nuclear burning stages, and it is incredibly hot, with surface temperatures reaching over 100,000 Kelvin. It is this searingly hot white dwarf at the centre of the Helix Nebula that acts like a cosmic ultraviolet light bulb, flooding the surrounding ejected gas with intense high-energy radiation. This radiation strips electrons from the atoms in the gas cloud, a process called ionization. And when those electrons eventually recombine with the atoms, they emit light at specific colours, causing the nebula to glow in those beautiful hues we see in photographs. The predominant red colour often comes from ionized hydrogen, while green-blue tints can come from ionized oxygen. So, the gorgeous structure of the helix is not just a static cloud, it is a luminous, energized shell of stellar material, illuminated from within by the stellar corpse it surrounds. This entire sequence, from red giant to planetary nebula to white dwarf, is a universal fate for stars with masses between about 1 and 8 times that of our Sun. Stars much more massive than that will end their lives in a supernova explosion, leaving behind a neutron star or black hole. But for Sun-like stars, this is the standard retirement plan. The term planetary nebula is therefore a relic of observational history, a label that stuck even after we understood its true nature. The physics behind this transformation is governed by fundamental principles of stellar evolution and thermodynamics. As the red giant loses its outer layers, the rate of mass loss can be tremendous, with the star ejecting a significant fraction of its total mass into space. This ejected material moves outward at speeds of tens of kilometers per second, creating the expanding shell we observe. The shape of the nebula can be complex. While some, like the helix, appear roughly spherical, many others show bipolar or butterfly shapes, likely influenced by binary companion stars or strong magnetic fields during the ejection process. The helix itself shows subtle bipolar characteristics and a complex filamentary structure, indicating that its formation was not a perfectly symmetric event. The energy output from the white dwarf is crucial. Without it, the nebula would not glow visibly and would be much harder to detect. This phase of a star's life is relatively brief on cosmic timescales, lasting only about 10,000 to 20,000 years before the expanding gas cloud becomes too diffuse and faint to see, and the white dwarf slowly cools down over billions of years. During this brief window, however, the planetary nebula plays a critical role in the chemical evolution of the galaxy. The ejected material is enriched with heavy elements that were forged inside the star during its lifetime through nuclear fusion processes. Elements like carbon, nitrogen, and oxygen are spewed out into the interstellar medium, mixing with other gas and dust clouds. This enriched material will eventually become part of new generations of stars, planets, and possibly even life. So, in a very real sense, the death of one star provides the raw ingredients for the birth of future solar systems. When we study the Helix Nebula, we are effectively conducting an autopsy on a dead star, analysing its chemical composition to understand what elements were produced and how they are being recycled. Spectroscopic observations allow astronomers to determine the abundances of different elements in the nebula, telling the story of the star's nuclear burning history. For instance, the presence of certain elements can reveal whether the star underwent specific fusion stages like helium burning or the triple alpha process. The helix dot, being so close to us, offers an unparalleled detailed view of this process. The white dwarf at its centre is a fascinating object in its own right. It packs a mass comparable to the Sun into a volume about the size of Earth, making it incredibly dense. A single teaspoon of white dwarf material would weigh several tons on Earth. This dwarf will continue to radiate heat for eons, gradually cooling and dimming until it becomes a cold, dark black dwarf. Though the universe is not yet old enough for any black dwarfs to exist, understanding planetary nebulae like the Helix also helps astronomers calibrate distance measurements in the universe and study the physics of gas dynamics and radiation hydrodynamics. The interaction between the fast wind from the hot white dwarf and the slower wind from the earlier red giant phase can shape the nebula and create intricate structures. In the Helix, this is evident in the cometary knots, which are dense globules of gas and dust that are being photoevaporated by the intense radiation, forming tails that point away from the central star. Each of these knots is roughly the size of our solar system, showcasing the immense scale of the nebula. So, when you look at the Helix Nebula, you are witnessing a universal recycling program, a transformative event that marks the end of one stellar life and the beginning of countless others. It is a powerful reminder that the cosmos is in a constant state of change, with stars being born, living out their lives, and dying, all while contributing to the grand cycle of matter and energy. This knowledge transforms the Helix from a mere pretty picture into a profound scientific narrative about how stars work and how the elements that make up our world came to be. The next time you gaze at its image, remember that you are looking at the future of our own sun, a destiny that awaits it in about 5 billion years, when it too will shed its outer layers and create its own planetary nebula, briefly lighting up the cosmos before fading into the darkness, leaving behind a white dwarf as its lasting memorial. This connection between the distant Helix and our own solar system makes the study of these objects not just an academic exercise, but a way to understand our own origins and ultimate fate in the universe. The physics of stellar death is thus a key chapter in the story of cosmic evolution, and the Helix Nebula serves as one of its most eloquent and accessible illustrations. At the very heart of that expanding cloud of gas, right where you would expect the pupil to be in that cosmic eye, sits the incredible engine of the entire system, the central white dwarf. And understanding this stellar remnant is key to appreciating the full picture of the Helix Nebula's story. This white dwarf is all that remains of the star's original core, a superheated and unbelievably dense ball of matter that is now slowly cooling down over billions of years. When the star shed its outer layers to form the beautiful nebula we see, the core was left behind, no longer supported by the outward pressure of nuclear fusion, and it collapsed under its own immense gravity. The result is an object with a mass roughly comparable to our Sun's, but compressed into a volume no bigger than our planet Earth, which is an almost unimaginable density. To put that into perspective, if you could bring a single sugar cube-sized piece of this white dwarf to Earth, It would weigh as much as an elephant, or several tons, because the matter is so tightly packed together. This incredible density is due to a state of matter called electron degeneracy pressure, where electrons are squeezed together as much as quantum physics will allow, preventing further collapse but creating an object of phenomenal compactness. The temperature of this white dwarf is equally extreme, with surface temperatures soaring to over 100,000 Kelvin, making it far hotter than our Sun, which has a surface temperature of only about 5,800 Kelvin. This intense heat is a leftover from the star's earlier life and the violent collapse of its core, and it is this heat that drives the next crucial phase. The white dwarf acts as a powerful ultraviolet lamp, flooding the surrounding nebula with high-energy radiation that slams into the ejected gas clouds. This radiation is so energetic that it strips electrons away from the atoms in the gas, a process known as ionization. And it is this ionization that causes the nebula to glow in those spectacular colours we observe through telescopes. Without this central white dwarf pumping energy into the system, the Helix Nebula would be a dark, cold cloud of gas, invisible to our eyes and instruments. So it is truly the heart that gives the nebula its visible life. The discovery and ongoing study of this central star have been fundamental to validating our models of stellar evolution, confirming predictions about the end stages of Sun-like stars. By analysing the light from this white dwarf using spectroscopy, astronomers can determine its chemical composition, which turns out to be rich in carbon and oxygen, the ashes left over from the helium fusion processes that occurred in the star's final stages. These elements were forged in the star's interior during its life and are now exposed, telling us a detailed story about the nuclear reactions that powered it. The white dwarf is not perfectly stable. It may have variations in its brightness or exhibit signs of a residual atmosphere, and studying these details helps scientists understand the complex processes during the transition from red giant to white dwarf. One fascinating aspect is the potential presence of accretion disks or material still falling onto the white dwarf, though in the case of the Helix, the nebula is largely clear, suggesting the major ejection phase is over. The gravity on the surface of this white dwarf is phenomenally strong, hundreds of thousands of times greater than Earth's gravity, which would crush any known material instantly. This immense gravity also affects the light escaping from it, causing a gravitational redshift that can be measured to confirm theories of general relativity. As the white dwarf continues to shine, it is destined to cool down slowly over trillions of years, eventually fading to a cold, black dwarf, though the universe is not yet old enough for any black dwarfs to exist. The role of this central remnant extends beyond just lighting up the nebula. It also influences the structure and dynamics of the entire system. The fast wind of particles streaming from the white dwarf interacts with the slower moving material ejected earlier, helping to shape the nebula and create features like the complex filaments and the cometary knots. These knots, which are dense globules of gas and dust, are being eroded by the intense radiation from the white dwarf, forming tails that point radially away from it, and their survival depends on the balance between this radiation pressure and their own density. Studying the white dwarf's output helps astronomers model this photoevaporation process and understand how such structures can persist in such a hostile environment. The distance to the Helix Nebula, dot, about 650 light-years, allows for relatively detailed observations of this central star, making it a prime laboratory for white dwarf physics. Observations across different wavelengths, from ultraviolet to X-rays, reveal the high-energy processes at work, with the extreme ultraviolet radiation being particularly important for ionizing the nebula. In X-rays, Scientists can sometimes detect emission from the hot corona of the white dwarf or from accretion processes, providing clues about its magnetic activity and rotation. The white dwarf in the helix is also a reminder of our own sun's future. In about 5 billion years, after going through its red giant phase, the sun will leave behind a similar white dwarf, surrounded by its own planetary nebula, though it might look different due to variations in mass and ejection history. This connection makes the study of the helix's central star not just an academic pursuit, but a way to peer into the destiny of our own solar system. The chemical composition of the white dwarf, rich in carbon and oxygen, also has implications for the enrichment of the interstellar medium, as these elements will be dispersed and incorporated into new stars and planets. This recycling process is crucial for the chemical evolution of galaxies, and white dwarfs like this one are key agents in that cycle. Despite its small size, the white dwarf contains a significant fraction of the original star's mass, with the rest being expelled into the nebula, and tracking how this mass is distributed helps refine models of mass loss in aging stars. The age of the white dwarf can be estimated from its cooling rate, and for the helix, it is thought to be relatively young, perhaps only around 10,000 years old, which is consistent with the nebula's expansion age. As it cools, its colour will change, shifting from blue-white to redder hues over time. Though this process is incredibly slow, the study of this white dwarf is also intertwined with the search for exoplanets. In some systems, white dwarfs are found to have planetary debris disks or even shredded planets, indicating that planetary systems can survive the stellar death process. While no planets have been confirmed around the helix's white dwarf, the presence of the cometary knots suggests that material exists that could potentially form new planetary bodies in the distant future. The intense radiation field around the white dwarf creates a harsh environment where complex molecules might be destroyed, but also where new chemical reactions can occur, contributing to the astrochemical diversity of the nebula. Understanding the white dwarf's properties requires sophisticated instruments, and telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope provide invaluable data on its spectrum and temperature. Amateur astronomers can even observe the central star with large enough telescopes under dark skies, though it appears as a faint point of light amidst the glow of the nebula. The white dwarf's position at the centre of the helix is not just coincidental. It is the gravitational anchor around which the entire nebula is organised, and its light echoes through the structure, illuminating the history of the star's death. As we continue to observe and analyse this central remnant, we learn more about the life cycles of stars, the forces that shape nebulae, and the ultimate fate of stellar objects. The Helix Nebula's white dwarf is a testament to the transformative power of stellar evolution, a tiny yet mighty relic that holds the secrets of its parent star's past and lights the way for future discoveries. Its study bridges the gap between theory and observation, helping to confirm that our understanding of stellar physics is on the right track. So, the next time you see an image of the Helix Nebula, remember that the brilliant glow is powered by that tiny, dense core at its centre, a white dwarf that continues to tell the story of a star's death and its lasting impact on the cosmos. This central heart, though small, is the key to unlocking the mysteries of the helix and countless other planetary nebulae, reminding us that even in death, stars leave behind a legacy that shapes the universe. While the central white dwarf serves as the powerful engine driving the entire system, the true marvel of the Helix Nebula unfolds when we examine its structure in detail, revealing a complexity that goes far beyond the simple, iconic eye shape we often see in popular images. Early observations might have depicted it as a smooth, round disk, but advanced telescopes have shown us that it is actually a tangled, intricate web of gas and dust, full of fascinating details that tell a deeper story about its formation. The nebula is composed of two main parts: a bright inner disk that is most visible in photographs, and a much larger, fainter outer halo that extends far beyond, which was created during different episodes of mass ejection from the dying star. This halo is evidence that the star did not shed its outer layers in one single event, but in several successive outbursts over time, each contributing to the nebula's overall architecture. One of the most striking features discovered within this structure are the countless cometary knots, which are dense clumps of gas and dust that look like tiny comets with glowing tails streaming away from the central star. Each of these knots is remarkably large, often comparable in size to our entire solar system, and they are scattered throughout the inner disk like cosmic pearls on a string. These knots are not solid objects, but rather globules of molecular hydrogen and dust that are significantly denser and colder than the surrounding gas, allowing them to withstand the intense radiation from the white dwarf for a time. The process that forms these tails is called photoevaporation, where the powerful ultraviolet light from the central star slowly boils away material from the knots, stripping off gas and dust and creating those spectacular, illuminated trails that point radially outward. It is estimated that there are over 20,000 of these knots within the helix, each acting as a small shield against the stellar wind and radiation, and their survival provides key insights into how matter behaves in such extreme environments. The presence of these structures indicates that the original ejection of material was not a smooth, uniform process, but rather a clumpy and chaotic one, where some regions of the outgoing gas were much denser than others. Beyond the knots, the nebula exhibits a subtle bipolar structure, meaning it is not perfectly spherical but slightly elongated, suggesting that the dying star might have had a companion star or was influenced by strong magnetic fields during its final phases. If a binary companion was present, its gravitational pull could have funneled the ejected material into a more hourglass-like shape, which is common in other planetary nebulae but less pronounced in the helix. Alternatively, the star's own magnetic fields could have directed the outflow, creating asymmetries that we now observe as faint lobes or extensions. This complexity is further highlighted by the filamentary patterns seen throughout the nebula, which are like delicate ribbons of gas that have been shaped and sculpted by various forces, including shocks from the fast wind from the white dwarf colliding with the slower moving material ejected earlier. The inner disk itself is not uniform. It has variations in brightness and texture, with some regions appearing brighter due to higher concentrations of ionized gas, while others are darker where dust obscures the light. Observations in different wavelengths of light, such as infrared, reveal even more structure, including a cold dust component in the halo that is invisible in optical light, showing that the nebula's extent is greater than what we can see with our eyes. The overall expansion of the nebula is not perfectly symmetric either. Measurements show that different parts are moving at slightly different speeds, with the inner regions expanding faster than the outer halo, which tells us about the history of the mass loss events. Studying this detailed architecture is like being a cosmic detective, piecing together the sequence of events that led to the star's death. By mapping the velocities and densities of the gas, astronomers can recreate the timeline of the eruptions, understanding how the star shed its layers over thousands of years. The cometary knots, in particular, serve as natural laboratories for studying processes like photodissociation and ionization, where molecules are broken apart by radiation, and they might even contain the seeds for future planetary systems, as their dense cores could potentially coalesce into new bodies over astronomical timescales. The intricate structure also has implications for the chemical enrichment of space, as the knots and filaments are rich in elements like carbon, oxygen, and nitrogen, which are being recycled into the interstellar medium. This recycling is crucial for the formation of new stars and planets, and the helix provides a nearby example of how this dispersal happens. The complexity of the Helix Nebula challenges the simple perception of planetary nebulae as mere bubbles or disks. It shows that they are dynamic, evolving entities with a rich internal life. Even the apparent symmetry of the eye is an illusion when viewed from our distant perspective. If we could see it from another angle, the bipolar nature might be more obvious. This understanding comes from comparing the helix to other planetary nebulae, which exhibit a wide range of shapes from spherical to highly bipolar. And studying these variations helps astronomers identify the physical parameters that influence their formation, such as the mass of the progenitor star, its rotation, and its magnetic field. In the case of the helix, the progenitor was likely a star similar to our Sun, and its relatively simple initial mass might explain why the bipolarity is subtle compared to nebulae from more massive stars. The filamentary structures and knots are not static. They are constantly changing, albeit on timescales much longer than human life. As the radiation from the white dwarf continues to erode and reshape them, over thousands of years, the knots will eventually dissipate, and the nebula will become more diffuse, fading from view as the gas spreads out into space. The current structure is thus a snapshot in time, capturing a brief phase in the long process of stellar evolution. For amateur astronomers and astrophotographers, capturing the full complexity of the helix requires patience and specialized equipment, such as filters that isolate the light from specific elements like oxygen and hydrogen, which highlight different parts of the nebula. Even with large telescopes, visual observers might only see the bright inner ring and miss the finer details. But photographs taken with long exposures unveil the hidden depths of its architecture. The study of this complexity is ongoing, with new telescopes like the James Webb Space Telescope providing unprecedented views in infrared light, penetrating the dust to reveal the cold, dense regions of the knots and halo in greater detail. These observations help answer open questions, such as why the knots are so abundant in the helix and how they manage to form and survive in such a hostile environment. The structure also holds clues about the earlier life of the star, including its red giant phase, when it experienced intense pulsations and mass loss that set the stage for the nebula we see today. By analysing the distribution and motion of the gas, scientists can infer the properties of those pre-planetary nebula stages, filling in gaps in our understanding of stellar death. The Helix Nebula, therefore, is not just a beautiful object but a rich tapestry of physical processes, from hydrodynamics and radiation physics to chemistry and magnetism. Its complex structure reminds us that the universe is rarely simple, and even in death, stars create intricate and ordered patterns that reflect the fundamental laws of physics. So, the next time you see an image of the helix, look beyond the eye and appreciate the tangled beauty within, knowing that each filament and knot has a story to tell about the violent yet graceful end of a star. This deeper exploration into its anatomy not only satisfies our curiosity, but also advances our knowledge of cosmic evolution, connecting the death of one star to the birth of future generations and highlighting the interconnectedness of all things in the cosmos. The helix's structure is a testament to the dynamic and ever-changing nature of the universe, where simplicity on the surface often hides profound complexity beneath, diving right into one of the most intricate aspects of that hidden complexity we just touched upon. Let's talk about the countless cometary knots. those cosmic pearls that make the Helix Nebula so uniquely fascinating and detailed. These are not just random specks, they are dense, compact globules of gas and dust, each with a brilliant tail that streams away from the central star, making them look like a swarm of tiny comets frozen in space, which is exactly how they got their nickname. Imagine thousands of these structures, each one a self-contained world of molecular gas, primarily hydrogen, and dust, existing within the larger nebula, and each one acting as a tiny shield against the fierce ultraviolet radiation pouring out from the white dwarf at the heart of the system. What makes these knots so special is their incredible density and relatively low temperature compared to the surrounding nebula gas. They are like dense, cold pockets that have managed to condense out of the ejected material. And this density is what allows them to temporarily withstand the hostile environment. The process that shapes them is called photoevaporation, where the intense UV light from the central star slowly but relentlessly boils away material from the surface of each knot, stripping off atoms and molecules and creating those long, glowing tails that always point radially outward, away from the source of radiation. This is a violent and ongoing process, with material being ablated from the knots and ionized, causing it to glow in specific colors that we can detect. And it is this very erosion that makes the tails visible to our telescopes. Each knot is surprisingly large, often comparable in size to our entire solar system, which gives you a sense of the immense scale we are dealing with here. And estimates suggest there are more than 20,000 of these knots scattered throughout the inner regions of the Helix Nebula. Their formation likely occurred during the chaotic ejection of the star's outer layers, when clumps of denser material coalesced amidst the expanding gas. And these clumps have persisted due to their higher density, which provides some protection against complete dispersal. The composition of these knots includes not only molecular hydrogen, but also other molecules and dust grains. And in some cases, more complex carbon-based molecules have been detected, which adds another layer to their astrochemical significance. The survival of these knots against the powerful radiation field is a key area of study, as it tells us about the balance between radiation pressure and gravitational or cohesive forces within the globules. Over time, the knots are being eroded, and their lifetimes are limited, perhaps on the order of tens of thousands of years, which is a blink of an eye in cosmic terms. But during this time, they serve as incredible natural laboratories by studying how the radiation affects them. Astronomers can learn about similar processes in other astrophysical contexts, such as in protoplanetary disks around young stars or in the interstellar medium. One of the most exciting implications of these cometary knots is their potential role in the formation of future planetary systems. The dense cores within these knots might contain enough material to eventually coalesce into new planets, planetesimals, or other solid bodies long after the nebula has dissipated. This idea of second-generation planet formation is profound because it suggests that the death of one star can provide the raw materials for new worlds around another star, effectively recycling elements on a galactic scale. The knots in the helix are particularly important for this line of research because their proximity allows for detailed observation, giving us a close-up view of processes that might be happening in more distant nebulae. Observations across different wavelengths, especially in infrared light, reveal the cold, dense cores of the knots, which are shielded from the UV radiation and where molecules can survive and even complex chemistry might occur. In fact, detections of molecules like water vapor and carbon monoxide in similar environments hint at the rich chemical diversity present. And while direct evidence of planet formation in the helix knots is not yet available, the theoretical framework supports the possibility. The study of these knots also helps astronomers understand the durability of protoplanetary disks in extreme environments. If knots can persist here, then perhaps similar structures could survive around young stars in harsh regions, influencing how planetary systems evolve. Moreover, the knots provide clues about the mass loss history of the progenitor star. Their distribution and properties can indicate the conditions during the ejection phases, such as the speed and asymmetry of the outflows. For instance, the alignment of the tails consistently away from the central star confirms the directionality of the radiation field and helps map the magnetic fields or flow patterns within the nebula. The sheer number of knots, over 20,000, suggests that the original mass ejection was not a smooth process, but rather a clumpy and fragmented one, with significant density variations in the expelled material. This clumpiness is common in planetary nebulae, but the Helix offers a clear case to study it in detail. From an observational perspective, capturing these knots requires high-resolution telescopes and often narrowband filters that isolate the light from specific ions, like ionized hydrogen or oxygen, which highlight the tails and the knots themselves. Amateur astronomers with advanced equipment can sometimes detect the overall structure of the nebula, but resolving individual knots is typically the domain of large professional telescopes like the Hubble Space Telescope, which has provided iconic images showing them in stunning detail. The future of studying these knots looks bright with instruments like the James Webb Space Telescope, whose infrared capabilities will peer into the densest parts of the knots, potentially revealing their chemical composition and internal structures like never before. Understanding the photoevaporation process in these knots has broader implications. It is a classic example of radiation-matter interaction, and models developed here can be applied to other phenomena, such as the evaporation of protoplanetary disks or even the atmospheres of exoplanets close to their host stars. The knots also act as tracers for the physical conditions within the nebula by measuring their sizes, densities, and the rates at which they are being eroded. Scientists can infer the strength of the UV radiation field, the density of the surrounding gas, and the age of the nebula itself, despite their temporary nature. The cometary knots are a dynamic and integral part of the Helix Nebula's evolution, contributing to its overall appearance and serving as key components in the recycling of material. They remind us that even in death, stars create structures that can foster new beginnings, and the elements within these knots, carbon, oxygen, nitrogen, are the very building blocks of life, destined to be incorporated into future generations of stars and planets. So, when you look at an image of the Helix Nebula and see those tiny, tail-like features, remember that each one is a story of resilience and transformation, a small cosmic pearl in the vast ocean of space, holding secrets about the past and potential for the future. This deep dive into the cometary knots not only enhances our appreciation of the Helix's beauty, but also underscores the importance of detailed, close-up studies in advancing our knowledge of stellar life cycles and the continuous cycle of matter in the universe. Their existence bridges the gap between the death of a star and the birth of new celestial objects, making them a crucial piece in the puzzle of cosmic evolution. As research continues, each new discovery about these knots brings us closer to understanding how planetary systems, including our own, might have formed from similar processes long ago, and how they might form again in the future from the ashes of stars like the one that created the Helix Nebula. This exploration is a testament to the ever-surprising nature of the cosmos, where even the smallest features can hold the keys to unlocking grand mysteries, and the cometary knots of the helix are a perfect example of that profound truth. The story of those cometary knots and their intricate structures naturally leads us to the very ingredients that compose them: Because the Helix Nebula is not just a spectacle of shape and light, but a vast, open-air chemical laboratory where the elements forged inside a star are now being released and mixed in the depths of space. When astronomers point their spectrometers at the helix, they are essentially taking a chemical fingerprint, breaking down its light into a rainbow of colours that reveals the specific signatures of different elements and molecules. The dominant players in this cosmic chemistry set are hydrogen and helium, the two lightest and most abundant elements in the universe, which make up the bulk of the glowing gas you see in images. But the real story is told by the trace elements, the heavier atoms like oxygen, nitrogen, sulfur dot, and neon that are detected through their unique spectral lines. Each of these elements emits or absorbs light at very specific wavelengths when it is energized, acting like a barcode that scientists can read to determine not only what is there, but also in what quantities. The relative abundance of these elements is a direct record of the nuclear fusion processes that occurred during the star's lifetime, allowing astronomers to effectively perform an autopsy on the deceased star. For instance, the presence of significant amounts of oxygen and carbon tells us that the star progressed through the helium-burning phase in its core, fusing helium atoms into carbon and then some of that carbon capturing another helium nucleus to form oxygen. This process happened deep within the star's interior over billions of years, and now that the outer layers have been blown away, we can see the ashes of those nuclear fires exposed to space. Nitrogen is another key element, often enhanced in planetary nebulae due to processes that bring carbon-nitrogen-oxygen cycle products to the surface during the star's evolution. The detection of sulfur and neon provides additional clues, as these elements are produced in different stages of stellar nucleosynthesis, and their ratios help pin down the initial mass and specific history of the progenitor star. Beyond these individual atoms, the nebula is a site for molecule formation, with molecular hydrogen being detected in the colder, denser regions like the cometary knots, where two hydrogen atoms can bond together despite the harsh environment. Even more complex molecules have been found, including hints of carbon chains and, remarkably, fullerenes, which are large molecules of carbon arranged in hollow spheres like soccer balls. The discovery of fullerenes in the helix was a surprise, as these stable structures can form in the conditions present in the nebula, and their presence indicates a rich carbon chemistry that could be important for the origin of life elsewhere. The chemistry is not uniform throughout the nebula. Different regions show variations in composition, with the inner ionized region dominated by atomic ions and the outer cooler halo containing more molecules and dust. This diversity is driven by the intense radiation from the central white dwarf, which ionizes atoms in its immediate vicinity but allows molecules to survive in shielded pockets. The process of ionization is crucial for the nebula's glow. When ultraviolet photons from the white dwarf strike a hydrogen atom, they knock off an electron, and when that electron eventually recombines with a proton, it emits a photon of red light, which is why hydrogen often appears red in images. Oxygen atoms, when ionized, can emit greenish-blue light, and combining these different emissions creates the false color images that are both beautiful and scientifically informative. This chemical enrichment is a key part of the galactic life cycle. The Helix Nebula is spewing out these newly forged heavy elements into the interstellar medium, where they will mix with other gas and dust clouds over millions of years. This enriched material will collapse under gravity to form new stars, planets, and eventually, perhaps, the building blocks of life. In fact, the carbon, oxygen, and nitrogen we see in the helix are the same elements that make up our own bodies and our world. so we are literally made of stardust from objects like this. The nebula is thus not just a tomb for a dead star, but a nursery for future cosmic generations, recycling material that will one day be part of other solar systems. Studying the chemistry of the helix also helps astronomers understand the chemical evolution of galaxies over time, as each generation of stars contributes more heavy elements to the mix, making subsequent generations of stars and planets more metal-rich. This is important for understanding how planets like Earth formed and why they have the compositions they do. The techniques used to study the helix's chemistry, such as spectroscopy, are the same tools used to analyse the atmospheres of exoplanets, linking the death of one star to the potential for life around others. For amateur astronomers, while you cannot perform spectroscopy easily, knowing that the faint glow you see is a tapestry of elemental signatures adds a deeper layer of appreciation to the view. The chemical story of the helix is still being written, with new molecules and elements being detected as telescope technology improves, and each discovery adds a piece to the puzzle of how stars live and die. This ongoing research highlights the dynamic nature of the cosmos, where chemistry plays a central role in shaping the universe we see today. So, the next time you gaze at an image of the Helix Nebula, remember that you are looking at a cosmic element factory, a place where the raw materials for worlds and life are being scattered across space, continuing the cycle of birth, death, and rebirth that defines our galaxy. This chemical perspective transforms the nebula from a mere visual marvel into a key chapter in the story of our cosmic origins, reminding us that we are connected to the stars not just by light, but by the very atoms that compose us. The Helix Nebula, therefore, serves as a powerful reminder of the interconnectedness of all things in the universe, where the death of a star fuels the birth of new possibilities, and its chemical signature is a lasting testament to the processes that make life possible. Understanding how those chemical elements are dispersed naturally brings us to the next chapter in the story, which is the relentless passage of time and how it is shaping the Helix Nebula right now. Because this beautiful object is not a frozen snapshot in space, but a dynamically evolving system. Even if that evolution is imperceptibly slow from our human perspective, the entire structure is in a state of constant, albeit gradual, change, with the gases expanding outward and the central star cooling down. A process that began millennia ago and will continue for eons to come. Current estimates suggest that the initial ejection of the star's outer layers, the event that created the nebula we see, started approximately 10,000 years ago, which means that when humans were first developing agriculture and building the earliest civilizations, this star was in its death throes, casting off its atmosphere into the void. Since that moment, the nebula has been steadily expanding, and it will continue to do so for several more thousand years, growing larger and more diffuse with each passing century. As it expands, the gas and dust spread out over a greater volume, causing the overall density to drop, and this has a direct impact on how bright the nebula appears to us. The surface brightness, dot, or the amount of light emitted per unit area, is gradually decreasing because the same number of atoms are being spread thinner, making the nebula fainter over time. This fading is accelerated by the fact that the central white dwarf, the engine that ionizes the gas and makes it glow, is itself cooling down. That white dwarf started out incredibly hot, with temperatures over 100,000 Kelvin, but it has no internal fusion to keep it warm, so it is slowly radiating away its residual heat into space. This cooling process is inexorable and slow. Over billions of years, it will dim and redden, eventually becoming a cold, dark stellar remnant known as a black dwarf. though the universe is not yet old enough for any black dwarfs to exist, as it would take many trillions of years for a white dwarf to cool completely. So, the nebula's visibility has a limited window. In another 10,000 years or so, it might become too faint to be easily observed from Earth. As the gas disperses into the interstellar medium and the light fades, the expansion itself is not uniform. Different parts of the nebula are moving at different speeds, with the inner regions expanding faster than the outer halo, which tells astronomers about the history of the mass loss. By measuring these expansion velocities using spectroscopy, scientists can rewind the clock and reconstruct the timeline of the ejection, understanding how the star shed its layers in successive waves. This kinematic modelling is crucial because it allows us to predict not only the future of the helix, but also the fate of other planetary nebulae, helping us understand their role in the galactic ecosystem. Planetary nebulae like the helix are transient phenomena, acting as brief but important recycling stations in the galaxy. They take the enriched material from a star's interior and spew it out into space, where it can eventually collapse to form new stars, planets, and perhaps even life. But this phase is short-lived on cosmic scales. After the nebula dissipates, the white dwarf remains as a long-lasting monument, silently cooling in the dark. The evolution of the Helix Nebula is therefore a story in several acts. The dramatic ejection, the brilliant ionization phase we see now, the slow fading as the gas expands and the white dwarf cools, and the final dissolution into the background of space. For amateur astronomers, this means that the view through telescopes is a precious glimpse into a cosmic event that is actively unfolding, even if we cannot perceive the change in a single lifetime. The fact that we see the nebula as it was 650 years ago, due to the light travel time, adds another layer to this temporal narrative. We are observing the past, and any changes happening there now will not be visible to us for centuries. This time delay is a fundamental aspect of astronomy, reminding us that we are always looking back in time when we gaze at the stars. Scientists use computer models to simulate this evolution, inputting data on the nebula's current size, density, expansion speed, and the white dwarf's temperature to forecast how it will look in the future. These models help validate theories of stellar evolution and ensure that our understanding of physics holds up over astronomical timescales. The helix serves as a key calibration point for such models because it is one of the closest and best studied planetary nebulae. As the nebula expands, its interaction with the surrounding interstellar medium also plays a role. The outgoing gas can sweep up ambient material, creating shock fronts and additional structures, though in the case of the helix, this effect is minimal due to the low density of the local space. The cometary knots we discussed earlier are also part of this evolutionary story. They are temporary features that will eventually be eroded away by the radiation, their material blending into the expanding shell. Their lifetimes are estimated to be on the order of tens of thousands of years, after which they will vanish, leaving no trace. This gradual dissipation means that the iconic eye shape will become less defined over time, blurring into a faint, amorphous cloud. The timeline for the helix's visibility is thus set by two factors: the expansion and dilution of the gas, and the cooling of the white dwarf. Once the white dwarf cools below a certain temperature, it will no longer emit enough ultraviolet radiation to ionize the gas, and the nebula will cease to glow, becoming dark and invisible at optical wavelengths. At that point, only infrared telescopes might detect the cold dust and molecular gas, but the spectacular colours will be gone. This fate awaits all planetary nebulae, making them fleeting beauties in the cosmic landscape. The study of the helix's evolution also ties into the life cycle of stars in our galaxy. By observing how quickly it is fading, astronomers can estimate the rate at which such nebulae contribute heavy elements to the interstellar medium, enriching the galaxy for future generations. This enrichment is a continuous process, with countless stars undergoing similar transformations, each adding their own chemical signature to the mix. The helix dot, being so close, allows us to quantify this process with great accuracy. For those interested in astrophotography, capturing the helix now is capturing a moment in its long decline, a snapshot of a phenomenon that will not last forever. The images we take today will become historical records for future astronomers, who might look back and see how the nebula has changed over centuries or millennia. This long-term perspective is what makes astronomy so fascinating. It connects us to the past and the future in a way few other sciences can. So, while the Helix Nebula appears eternal and unchanging in our brief lives, it is in fact a dynamic entity on a journey of dissolution, reminding us of the impermanence of all things in the universe, even the most stunning cosmic structures. Its story is a powerful illustration of the cycles of birth, life, and death that govern the cosmos, and by watching it evolve, we gain a deeper appreciation for our own place in this ever-changing tapestry. The gradual fading of the helix is not an end, but a transformation, as its material journeys on to seed new beginnings elsewhere in the galaxy, continuing the great cycle of stellar evolution that has been unfolding for billions of years and will continue for billions more. Watching the Helix Nebula evolve and fade over millennia inevitably leads to a profoundly personal realization. We are looking at a preview of our own solar system's destiny, a cosmic mirror reflecting the future that awaits our sun and its planets. The star that created the helix was a sun-like star, and its death throes provide the most detailed blueprint we have for what will happen here in about 5 billion years. Our sun is currently a stable, middle-aged star, fusing hydrogen into helium in its core, but this phase cannot last forever. In approximately 5 billion years, the sun will exhaust the hydrogen fuel in its core, triggering a catastrophic series of events that will utterly transform our solar system. The core, no longer supported by the outward pressure of fusion, will begin to contract under its own immense gravity, heating up dramatically. Meanwhile, the outer layers of the sun will respond by expanding outward at an astonishing rate, swelling to engulf the inner planets. This transformation into a red giant will see the sun grow to a diameter that could extend beyond the orbit of Earth, meaning our planet faces two possible fates. It will either be completely engulfed and vaporized within the sun's tenuous outer atmosphere, or it will be scorched beyond recognition, its oceans boiled away and its crust melted, as it orbits perilously close to the stellar surface. Mercury and Venus will certainly be consumed during this expansion. This red giant phase will be relatively brief, lasting only around 1 billion years. But it will be a time of incredible violence and change for whatever remains of the solar system. Eventually, the sun will become unstable, pulsating and shaking off its outer layers into space in a series of powerful outbursts, much like the star that created the helix did. These ejected layers will form a vast, expanding shell of gas and dust around the dying star, creating a new planetary nebula, a final, beautiful shroud for the stellar corpse. At the heart of this new nebula will be the sun's core, collapsed into a white dwarf, an Earth-sized object of incredible density that will initially be searingly hot, lighting up the surrounding gas for tens of thousands of years. This future nebula will likely be visible from other star systems, a fleeting memorial to our sun's long life. The comparison between the helix and the projected fate of our Sun is not just poetic, it is a critical scientific tool. By studying the details of the helix, its size, mass, chemical composition, and expansion rate, astronomers can calibrate and refine their computer models of stellar evolution. They can check if their theories about the mass loss rates, ejection mechanisms, and ionization processes are accurate by comparing them to this nearby, well-observed example. This helps them make more precise predictions about the timeline and characteristics of our own Sun's demise. For instance, the helix's complex structure, with its cometary knots and faint halo, informs models about how the Sun's mass loss might occur in clumps and waves, rather than a smooth, uniform flow. The presence of certain elements in the helix tells us what the Sun's chemical signature will be when it dies, revealing which elements forged in its interior will be returned to the galaxy. This direct comparison allows scientists to answer questions like how massive the Sun's planetary nebula will be, how long it will last, and how brightly it will shine. This knowledge is fundamental to astrophysics, as it tests our understanding of how stars of a certain mass live and die, beyond the pure physics. This analogy forces a deep, almost existential reflection on transience and our place in the cosmos. The Helix Nebula shows us that planetary systems are not permanent. They have a life cycle, and our own is no exception. The Earth, with all its history and life, exists within a narrow, stable window in the Sun's multi-billion-year lifespan. The emergence of life and intelligence here is a beautiful, but likely temporary, phenomenon in the face of these grand cosmic cycles. It highlights the fragility of our world and the uniqueness of our current era. This is not a cause for despair, but rather a perspective that can inspire a greater appreciation for the time we have and the remarkable fact that we are here to understand these processes at all. Our ability to observe a distant nebula, decipher its history, and connect it to our own future is a testament to human curiosity and intelligence. We are the universe becoming self-aware, looking out at its own workings and contemplating its own fate. The story of the helix and the Sun also underscores the interconnectedness of the cosmos. The elements that make up our planets and our bodies were created in the hearts of long-dead stars and scattered by events just like the one that formed the Helix Nebula. We are literally made from the remnants of stellar deaths. The death of our Sun, in turn, will enrich the surrounding interstellar medium with new, heavy elements, seeding future generations of stars and planets. One day, those elements may become part of new worlds and, perhaps, new life. So, while the demise of our solar system is a certainty on a long enough timeline, it is not an end but a transformation, a recycling of matter on a galactic scale. The Helix Nebula, therefore, is more than just a scientific case study. It is a profound teaching tool. It connects the abstract concepts of stellar physics to a tangible, emotional reality. It tells us that the Sun is not a permanent fixture in our sky, but a dynamic star with a life cycle, and that its death, while far in the future, is an integral part of the story of our galaxy. For anyone who gazes at the helix, whether through a telescope or in a photograph, it offers a chance to contemplate deep time and the ultimate fate of our home star system. It is a humbling and awe-inspiring vision, a reminder of the power and scale of the universe, and the incredible journey that matter undertakes from stellar death to planetary birth and, just maybe, to life itself. This knowledge empowers us to see our world not as an isolated stage, but as a participant in a vast, ongoing cosmic drama, where the end of one act simply sets the stage for the next. To truly understand the Helix Nebula, you have to look beyond what our eyes can see, because its full story is written across the entire electromagnetic spectrum, with each type of light revealing a different chapter of this cosmic drama. The beautiful visible light images, the ones that show the iconic green and red eye, only tell part of the tale. They show us the gas that is currently being energized by the central star, but they miss the colder dust, the hotter plasma, and the specific molecules that make up this complex object. When astronomers point infrared telescopes, like the Spitzer Space Telescope, toward the helix, they can peer through the outer layers of glowing gas to see the colder material that is invisible in optical light. Infrared light is essentially heat radiation, so it is perfect for detecting the vast amounts of coal dust and the dense, frigid cores of the cometary knots that are shielded from the star's intense ultraviolet glare. These observations reveal a much larger and more extensive halo around the nebula than we can see in visible light, a halo that was created during earlier, quieter mass loss episodes from the dying star long before the dramatic ejection that formed the main nebula. This tells us that the star's death was a long, drawn-out process, not a single explosive event. Furthermore, infrared data allows scientists to study the composition of the dust grains themselves, which include silicates and complex carbon-rich compounds, providing clues about the chemistry that occurred in the star's atmosphere before it was expelled. On the opposite end of the spectrum, observations in the ultraviolet and extreme ultraviolet range are crucial for studying the most energetic processes. The central white dwarf is blazingly hot and emits a tremendous amount of its energy in the UV part of the spectrum, and by analysing this light, we can determine the star's precise temperature, surface gravity, dot, and composition. Ultraviolet telescopes also allow us to see the very hottest gas in the nebula, plasma that is so energized it emits light our eyes cannot see, filling in the gaps of the ionization structure and helping us understand how efficiently the white dwarf is lighting up its surroundings. Even X-ray observations have been used to study the helix, detecting the high-energy processes associated with the shock-heated gas from the fast stellar wind colliding with the slower-moving ejected material. Meanwhile, radio telescopes offer an entirely different perspective, one tuned to the vibrations of molecules. By observing at specific radio wavelengths, astronomers can map the distribution of molecules like carbon monoxide and molecular hydrogen within the nebula, especially within the dense, cold cometary knots. This is vital because these molecules are the building blocks for more complex structures and can survive in environments where individual atoms would be torn apart. Radio observations help us understand the mass, density, and temperature of these knots and trace the dynamics of the gas as it expands into space. Each part of the spectrum is like a different instrument in an orchestra, playing its own unique part, and only when you listen to all of them together do you hear the full symphony. For example, dot. While a visible light image shows the glowing structure of the ionized gas, an infrared image overlays the cold dust and the full extent of the halo, and a radio map highlights the locations of dense molecular gas. Combining these multi-wavelength datasets allows astronomers to create a comprehensive dot, three-dimensional model of the nebula, understanding not just what it looks like, but how it works, how it is evolving, and how all its components interact. This approach is fundamental to modern astronomy. No single type of light can give us the complete picture. The technology required to see in these different wavelengths is also incredibly diverse, from space-based telescopes that orbit above Earth's atmosphere, which blocks most infrared, ultraviolet, and X-ray light, to massive radio dish arrays on the ground that combine their signals to achieve incredible resolution. The Helix Nebula has been a prime target for many of these great observatories, including Hubble for visible and ultraviolet light, Spitzer and now the James Webb Space Telescope for infrared, XMM Newton and Chandra for X-rays, and ground-based radio telescopes like the Atacama Large Millimeter Array, the James Webb Space Telescope, with its powerful infrared instruments, is particularly revolutionary for studying objects like the helix because it can see through the dust that obscures our view in visible light, directly imaging the dense cores of the cometary knots and analysing the chemical makeup of the cold gas in the outer halo. This multi-wavelength strategy also helps solve specific mysteries, such as the total mass of the nebula. Visible light observations alone can underestimate the mass because they miss the cold, neutral gas and dust. But by adding infrared and radio data, scientists can get a much more accurate measurement, which is crucial for understanding how much material the star actually ejected. It also helps us understand the energy balance within the nebula, quantifying how much energy the white dwarf is outputting and how that energy is absorbed, reflected, and re-emitted by the gas and dust around it. For the amateur astronomer or the casual space enthusiast, this means that the beautiful pictures we see are often composite images, artfully combining data from different telescopes and different wavelengths to create a single, informative, and visually stunning portrait. The colours in these images are often false colours, chosen to represent the different elements or physical processes being highlighted, but they are no less real in terms of the scientific information they convey. They are a translation of invisible light into a language our eyes can understand. This holistic, multi-wavelength approach is what transforms the Helix Nebula from a simple photograph into a rich, data-filled case study, allowing us to dissect its anatomy, understand its physiology, and trace its life history from a quiet star to a brilliant nebula to a fading cloud. It is a perfect example of how modern astrophysics works, relying on a fleet of telescopes across the globe and in space, each designed to see a different slice of the cosmic light show, to piece together the complete story of the universe around us. So the next time you admire an image of the helix, remember that it is just one frame from a much larger movie, a single voice in a cosmic choir, and that its true beauty and complexity are only fully revealed when we listen to all the light it has to offer. The ability to see the Helix Nebula across all those different wavelengths, from radio to X-rays, is a testament to the incredible technological journey that astronomy has undertaken over the centuries. And this evolution in imaging technology is a story worth telling in itself. Our view of the helix has transformed dramatically from a faint, fuzzy smudge in an eyepiece to the intricate, detailed portraits we see today, and each leap in technology has peeled back another layer of its mystery. In the early 19th century, astronomers like Carl Ludwig Harding peered through relatively small refracting telescopes, with lenses only a few inches across, and what they saw was a nebulous, diffuse patch of light that was difficult to distinguish from a comet or a distant star cluster. Their observations were recorded not with cameras, but with hand-drawn sketches, which were subjective and limited by the human eye and the stability of the atmosphere. These early telescopes suffered from chromatic aberration and other optical imperfections, making it hard to resolve any detail. And the helix was often just a note in a logbook, a curiosity among many. The introduction of astronomical photography in the late 19th and early 20th centuries marked a revolutionary shift. For the first time, light could be accumulated on a photographic plate over long exposures, capturing far more detail than the human eye could see in a single glance. This allowed the basic structure of the helix to emerge, revealing its circular form and earning it the early nickname that hinted at its planetary-like appearance. Though the term was a misnomer, photographic plates were more objective and permanent, enabling comparisons and measurements that sketches could not provide. And as emulsions improved and telescopes grew larger, the images became sharper. The move from refractors to large reflecting telescopes, like those built by William Herschel and later others, provided greater light-gathering power and reduced optical aberrations, allowing astronomers to study fainter objects and finer details. Throughout the mid-20th century, ground-based observatories with ever larger mirrors continued to refine our view, but Earth's atmosphere always posed a limit, blurring the images and hiding the nebula's subtlest features. The real game-changer arrived with the era of space telescopes, free from the distorting effects of the atmosphere, and the Hubble Space Telescope became the icon of this new age. When Hubble turned its gaze to the Helix Nebula in the early 2000s, it used its precise optics and sensitive instruments to capture images that stunned the world, revealing the thousands of cometary knots, the complex filamentary structures, and the delicate texture of the gas in unprecedented clarity. Hubble's cameras, like the advanced camera for surveys, could take long, stable exposures in visible and ultraviolet light, resolving details that were previously mere speculation, and its data allowed scientists to create three-dimensional models of the nebula's structure. But Hubble did not work alone. Ground-based telescopes like the Very Large Telescope in Chile complemented these observations with high-resolution spectroscopy, breaking down the light from the nebula into its constituent colors to analyze the chemical composition, velocities, and densities of the gas. These spectroscopic observations revealed the expansion speeds, the elemental abundances, and the physical conditions within the knots, providing crucial data to test theories of stellar evolution. The technology behind these ground-based telescopes also advanced rapidly, with adaptive optic systems that use deformable mirrors to correct for atmospheric turbulence in real time, producing images from Earth that rival those from space in sharpness. Meanwhile, infrared astronomy opened a new window, with telescopes like the Spitzer Space Telescope detecting the heat from cold dust and molecular gas, mapping the extensive halo and the dense cores of the knots that were invisible to Hubble. Spitzer's infrared eyes showed that the helix was much larger and more complex than it appeared in visible light, and it helped identify the presence of complex molecules, including fullerenes. The collaboration between space-based and ground-based observatories created a multi-wavelength synergy, where each facility addressed questions the others could not, building a holistic understanding. Now, we stand on the brink of another technological leap with the James Webb Space Telescope, which is designed to excel in the infrared part of the spectrum with a primary mirror much larger than Hubble's and instruments sensitive to the faintest heat signals. James Webb can peer through the veils of dust that obscure the inner workings of the helix, studying the molecular hydrogen and other compounds in the knots with clarity never before possible. And it can analyze the light from the central white dwarf to understand its cooling process. The data from James Webb is expected to resolve long-standing mysteries, such as the exact formation mechanism of the cometary knots and the detailed chemistry of the halo, potentially revealing the presence of water ice or other ices. This progression from hand-drawn sketches to digital sensors, from small lenses to massive segmented mirrors, reflects a broader story of human ingenuity and persistence. Each technological advance not only provided a better picture, but also forced us to revise our theories, showing that the helix was more dynamic and intricate than we ever imagined. The role of amateur astronomers in this technological narrative should not be overlooked. With increasingly affordable and powerful equipment, amateurs now contribute valuable observations, monitoring changes and capturing images that supplement professional research. The digital revolution, with CCD cameras and computer processing, has democratized astrophotography, allowing enthusiasts to stack hundreds of images to bring out details that were once the sole domain of large observatories. The software used to process these images, aligning and enhancing faint signals, is itself a form of technology that has transformed our visual access to the cosmos. Looking back, the journey from those first tentative observations to the forthcoming data from James Webb is a powerful reminder that our understanding of the universe is deeply intertwined with the tools we create. The Helix Nebula has been a constant subject, but our perception of it has been utterly transformed by technology, and as we develop new instruments. From giant ground-based telescopes like the Extremely Large Telescope to future space observatories, we can expect even more revelations. This ongoing technological evolution ensures that the Helix, and countless other celestial objects, will continue to surprise and educate us, proving that the quest to see farther and clearer is a fundamental part of the human spirit. The story of imaging the Helix is not just about better pictures. It is about deepening our comprehension of stellar life cycles, galactic ecology, and our place in the universe, all driven by the relentless march of technological progress. The incredible images captured by those advanced telescopes did more than just satisfy scientific curiosity. They catapulted the Helix Nebula from the pages of academic journals directly into the heart of popular culture, transforming it into a powerful symbol known to millions as the Eye of God. This nickname, while not scientifically accurate, resonated deeply with the public imagination, and its journey into the collective consciousness is a fascinating story of how science and culture intertwine. The moment those detailed pictures from the Hubble Space Telescope were released, showing a striking, eye-like structure with a dark central region and a glowing outer ring, people immediately saw something familiar and profound. This is a classic case of pareidolia, the same psychological phenomenon that makes us see faces in clouds or the man in the moon, where our brains are wired to recognize patterns, especially ones that resemble human features. The name Eye of God stuck because it was evocative, memorable, and tapped into universal themes, and it spread rapidly through media, the internet, and word of mouth. Soon, the Helix Nebula was no longer just NGC 7293. It became an icon, appearing in all sorts of creative and commercial contexts. You might have seen it on the cover of a science fiction novel, representing an ancient alien intelligence or a cosmic entity watching over the universe. It has featured in films and television shows, often used to signify something monumental, like a portal, a divine message, or the awe-inspiring scale of the cosmos. Music albums, particularly in genres like progressive rock or electronic music, have used its image to convey themes of infinity, mystery, and spiritual quest. Artists and graphic designers have incorporated the helix into their work, sometimes digitally altering the colors or composition to enhance its emotional impact, using it to explore ideas of creation, destruction, and the cycle of life. This cultural adoption turned the nebula into a versatile symbol. For some, it represents a benevolent, watchful presence, a kind of cosmic guardian. For others, it evokes a sense of being observed, a theme of surveillance or judgment, which ties into modern anxieties about technology and power. In some contexts, it is used to symbolize the end of times or an apocalyptic event, playing on its origin as a dying star. This wide range of interpretations shows how a single astronomical image can be adapted to fit different narratives and beliefs, becoming a blank canvas for human projection. The phenomenon also raises interesting questions about how scientific discoveries are communicated and perceived by the public. The official name, Helix Nebula, is descriptive of its structure but doesn't carry the same emotional weight, while the nickname Eye of God makes it accessible and emotionally charged, bridging the gap between complex astrophysics and everyday experience. This has undoubtedly helped spark interest in astronomy. Many people first learned about planetary nebulae because of this captivating name and image, leading them to explore more about space science. It serves as a gateway object, drawing people in with its beauty and mystery before they delve into the underlying physics of stellar evolution. The relationship between the scientific community and this popular interpretation is generally positive. Astronomers understand that such nicknames can engage the public and foster support for science funding, even if they strive for accuracy in their own work. The Helix's case is not unique. Other cosmic objects have similar stories, like the Pillars of Creation or the Sombrero Galaxy. But the Eye of God has a particularly strong hold on the cultural imagination due to its direct and powerful visual metaphor. Social media and the internet accelerated this process, with the image being shared, memed, and remixed countless times, each iteration reinforcing its status as a cultural touchstone. It appears in video games as a backdrop or a plot device, in advertising to suggest precision, vision, or cosmic scale, and in spiritual or New Age contexts as a symbol of universal consciousness or divine connection. This cultural life of the Helix Nebula demonstrates how humanity seeks to find meaning and narrative in the impersonal vastness of space. We anthropomorphize the cosmos, assigning familiar shapes and stories to make it comprehensible and relevant to our lives. The nebula's journey into popular culture also highlights the power of imagery. Without those stunning photographs, it would likely have remained an obscure object known only to specialists. The technology that allowed us to see it in such detail is the same technology that enabled its cultural ascent. Furthermore, the nickname has occasionally led to misunderstandings, with some mistaking it for a literal eye or a religious sign, which underscores the importance of clear science communication to accompany these powerful images. Despite that, the overall effect has been beneficial, creating a shared reference point that connects people across different backgrounds to the wonders of the universe. The Helix Nebula, as the Eye of God, has become more than an astronomical object. It is a piece of modern mythology, a symbol that evolves with our culture and reflects our current hopes, fears, and curiosities. It shows how science and art are not separate realms but constantly influence each other, with scientific discovery feeding artistic expression and cultural interest, in turn, inspiring further scientific exploration. For educators and communicators, the Helix is a perfect example of how to use a compelling hook to teach complex concepts, from the life cycle of stars to the scale of the galaxy. Its story in popular culture is still being written, as new generations discover it through different media, and it will likely continue to inspire and fascinate for years to come. So, the next time you come across that image in a movie, on a t-shirt, or in a song, remember that you are witnessing a unique collaboration between human perception and cosmic reality, where a cloud of gas 650 light-years away has become a mirror for our own dreams and questions. This cultural journey of the Helix Nebula reminds us that the universe is not just something we study from a distance. It is something we live with, interpret, and weave into the fabric of our shared human story, proving that the stars above are deeply connected to the stories we tell here on Earth. Despite its widespread fame and the cultural symbolism we just explored, the Helix Nebula remains a source of profound mystery for astronomers, with several key questions still open and actively debated in scientific circles, reminding us that our understanding of the cosmos is always a work in progress. One of the biggest puzzles involves the precise origin of its subtle bipolar structure, while it appears mostly circular to us. Detailed observations reveal it is not perfectly spherical but has a slight elongation, suggesting that the ejection of material was not symmetrical. This asymmetry could be explained by the influence of a binary companion star, where the gravitational pull of a second star could have funneled the gas into a more hourglass-like shape. But so far, no such companion has been definitively confirmed, leaving this as a compelling hypothesis. Alternatively, strong magnetic fields from the dying star itself might have shaped the outflow, but measuring these fields in such a distant, diffuse object is incredibly challenging with current technology. Another major enigma revolves around the thousands of cometary knots. We know they are dense globules of gas and dust, but the exact mechanism of their formation is not fully understood. Did they condense out of the ejected material as it expanded and cooled? Or were they pre-existing structures in the star's atmosphere that were carried outward? Furthermore, their survival against the intense ultraviolet radiation from the central white dwarf is remarkable, as this radiation should theoretically tear such clumps apart much faster than we observe. The process of photoevaporation, where the radiation slowly erodes the knots, creating their glowing tails, is studied, but models struggle to explain why they are so abundant and long-lived in the helix compared to other nebulae. The central white dwarf itself holds secrets, particularly regarding its detailed chemical composition and the complete history of mass loss from the progenitor star. By analysing the white dwarf spectrum, astronomers can infer the elements present, but uncertainties remain about the exact ratios and how they correlate with the star's nuclear burning phases. The history of mass loss during the star's final red giant phase is also murky. We see the evidence in the nebula's multiple shells and halos, but reconstructing the timeline and the triggers for the ejection events is complex. Did the star shed its layers in a steady wind or in violent, episodic outbursts? The answers lie in subtle details of the gas dynamics and chemistry that are still being decoded. The distance to the helix, while relatively close, is not known with pinpoint accuracy, and better distance measurements would help refine models of its physical size and expansion age. Another open question concerns the ionization structure. The way the ultraviolet light from the white dwarf illuminates and energizes the gas is understood in principle, but the fine-scale variations in brightness and density across the nebula suggest that the ionization process is more complex than simple models assume. The role of dust is another area of active research. Infrared observations show plenty of dust, but how it interacts with the gas and radiation, and how it affects the overall evolution of the nebula, is not fully quantified. The expansion of the nebula is another mystery. Measurements show that different parts are moving at different speeds, but the reasons for this velocity variation and how it relates to the initial ejection dynamics are still being investigated. The long-term fate of the cometary knots is also uncertain. Will they completely dissipate? Or could their dense cores collapse to form brown dwarfs or even planetary mass objects in the far future? This ties into broader questions about the formation of second-generation planetary systems from the debris of dead stars. The Helix Nebula is also a key object for studying the recycling of elements. While we know it enriches the interstellar medium, the efficiency of this process and how the ejected material mixes with surrounding gas are open areas of study. The interaction between the nebula and the interstellar medium is another puzzle. Is the nebula expanding into a vacuum? Or is it sweeping up ambient material and creating shock fronts that we have not yet detected? Observations in different wavelengths might reveal these interactions, but current data is incomplete. The age of the nebula is estimated to be around 10,000 years. But this is based on models that have uncertainties, and improved measurements could change our understanding of its evolutionary stage. The central white dwarf's cooling curve is another topic of interest, by studying how quickly it is cooling. Astronomers can test theories of white dwarf physics, but precise temperature measurements over time are needed. The possibility of a disk around the white dwarf, made from material that was not fully ejected, is also speculated, but no clear evidence has been found yet. The chemical diversity within the nebula is striking, with variations in element abundances from region to region. And explaining these variations requires a detailed reconstruction of the star's nucleosynthesis and mixing processes. The origin of the faint outer halo is another mystery. It suggests mass loss occurred long before the main ejection. But what triggered that earlier mass loss is not known. The role of rotation in the progenitor star is another factor. If the star was spinning rapidly, it could have influenced the shape of the nebula. But measuring the rotation of a star that no longer exists is impossible, so we rely on indirect clues. The magnetic fields, if present, could have played a role in shaping the nebula, but detecting and mapping these fields in a planetary nebula is extremely difficult with current instruments. The cometary knots themselves are like a swarm of miniature laboratories, but we do not fully understand why they are so uniformly distributed or what determines their sizes and densities. The photoevaporation process is modelled, but the models often do not match the observed tail lengths and lifetimes perfectly, indicating missing physics. The detection of complex molecules like fullerenes in the knots raises questions about the chemistry that can occur in such environments and whether these molecules could survive to seed new planetary systems. The link between the Helix and other planetary nebulae is also an open area. By comparing it to nebulae with different shapes and sizes, we can learn about the diversity of stellar deaths, but we need more data on a large sample of objects. The future observations with next-generation telescopes like the James Webb Space Telescope and the Extremely Large Telescope promise to address many of these mysteries by providing higher resolution and sensitivity. For instance, James Webb can probe the molecular content of the knots in unprecedented detail, potentially revealing the formation mechanisms. The ELT could directly image any potential companion star or resolve finer structures in the gas. These technological advances will undoubtedly bring new questions to light, as every answer in science tends to open up new mysteries. The ongoing study of the Helix Nebula is a testament to the iterative nature of scientific inquiry, where each discovery refines our models but also highlights the gaps in our knowledge. It reminds us that even for an object as well studied as the Helix, there is always more to learn, and that the pursuit of understanding is a never-ending journey. This keeps astronomy vibrant and exciting, as researchers around the world collaborate to piece together the puzzle of this cosmic eye. For amateur astronomers and enthusiasts, following these open questions can be just as thrilling as enjoying the beautiful images, because it connects us to the cutting edge of human exploration. So, while the Helix Nebula has become an icon in popular culture, its true value to science lies in the challenges it presents, driving us to build better telescopes, develop new theories, and ultimately, deepen our comprehension of the universe. The mysteries of the Helix are not just problems to be solved, they are invitations to curiosity, encouraging us to keep looking up and wondering about the secrets that the cosmos still holds. It is a fascinating paradox that the Helix Nebula, a definitive symbol of stellar death, might simultaneously be a crucial contributor to the very foundations for new life, making it an unexpectedly important object in the field of astrobiology, which is the study of life's potential in the universe. While it represents the end of a star, it is also a vast dispersal mechanism for the complex chemical building blocks that are essential for biology as we know it. Those thousands of cometary knots we have discussed are not just beautiful features, they are resilient repositories of organic chemistry, containing vast amounts of carbon-rich dust and complex molecules within these dense, shielded globules. Far from the destructive ultraviolet radiation at the nebula's immediate surface, molecules can form and survive. Astronomers have detected specific molecules in similar environments, including molecular hydrogen, carbon monoxide, and even more complex carbon-based compounds like polycyclic aromatic hydrocarbons, which are large, stable molecules made of carbon and hydrogen. The confirmed presence of fullerenes, which are soccer ball-shaped cages of carbon atoms, in the Helix Nebula is particularly significant because these structures are incredibly stable and could act as protective carriers for other molecules through the harsh conditions of interstellar space. This molecular inventory is crucial because these are the same types of compounds that are thought to have been delivered to the early Earth via comets and meteorites, potentially seeding our planet with the prebiotic ingredients necessary for life to emerge. The nebula is, in effect, performing a large-scale recycling operation. It is taking the elements forged in the interior of the star, carbon, oxygen, nitrogen, and combining them in its expanding shell to create more complex molecular structures. This enriched material is then ejected into the surrounding interstellar medium, where it mixes with other clouds of gas and dust. Over millions of years, this mixture will gravitationally collapse to form new stars and, crucially, new planetary systems. Any planets that form around these next-generation stars will already be seeded with these complex organic molecules, giving them a head start in the chemical processes that could eventually lead to life. The Helix Nebula provides a nearby, well-studied example of this galactic recycling process in action. By studying it, we can understand the mechanisms and efficiency with which a dying star enriches its neighbourhood. This helps us create models for how the raw materials for life are distributed throughout a galaxy. The proximity of the helix allows us to study this process in exquisite detail, serving as a template for understanding more distant, similar objects. The survival of these molecules in such a hostile environment is a key area of research. The knots act as protective cocoons, their density shielding the inner material from the full brunt of the central star's radiation. This demonstrates that prebiotic materials can be remarkably robust and can survive the violent phase of a star's death. This resilience increases the likelihood that such materials could be widely distributed across the cosmos. The implications are profound. If this process is common, which it should be given the vast number of sun-like stars in our galaxy alone, then the galaxy is continuously being seeded with the chemical precursors to life. Every similar stellar death contributes to a galactic reservoir of organic compounds. This means that planetary systems forming today, or in the future, might be born with a rich inheritance of life's building blocks from long-dead stars. Therefore, the study of planetary nebulae like the Helix is not just about death. It is fundamentally about the potential for new beginnings. It connects the grand cycle of stellar evolution directly to the possibility of biology elsewhere. When we search for habitable exoplanets or signs of life beyond Earth, we are indirectly relying on processes like those observed in the Helix to have provided the necessary chemical foundation. The nebula shows us that the elements that make up our own DNA and proteins were not only created in stars, but were also likely packaged and delivered in similar cosmic events. This creates a powerful link between the life cycle of stars and the origin of life itself. For astrobiologists, Objects like the Helix are natural laboratories to study the conditions that foster prebiotic chemistry. While the nebula itself is far too hostile for life to ever originate within it, the material it ejects will eventually become part of much colder, quieter, and more stable environments, the protoplanetary disks around newborn stars. In these calmer settings, the molecules forged and preserved in the nebula can undergo further chemical evolution, potentially leading to the formation of amino acids and nucleobases, the fundamental components of proteins and genetic material. So, while the Helix Nebula is a tomb for a star, it is also a testament to the incredible generative power of the universe. It illustrates that from death comes the potential for new life, on a scale that is truly galactic. This perspective transforms our understanding of such objects. They are not merely endpoints, but are vital way stations in the continuous cycle of cosmic matter. The carbon atoms in our bodies were likely part of a cloud similar to the Helix Nebula billions of years ago, having been expelled by a star that died long before our sun was born. This deep connection, revealed through the detailed study of objects like the Helix, underscores that we are not just observers of the cosmos, but active participants in its ongoing chemical and biological story. The astrobiological importance of the Helix Nebula thus lies in its role as a clear, observable link in the chain that connects stellar nucleosynthesis to the chemistry of life, proving that the ingredients for biology are a natural and widespread byproduct of stellar evolution. Watching those complex organic molecules drift away into the galaxy naturally makes you wonder about the forces propelling them. And this is where we can actually measure the nebula's ongoing motion, transforming our static image of the helix into a dynamic, expanding entity. Astronomers use a powerful technique called spectroscopy to do this, which involves analysing the light from the nebula to see how it has been stretched or compressed by the gas's movement. When the gas in the nebula moves towards us, the wavelengths of light it emits get squeezed together, shifting them toward the blue end of the spectrum, a phenomenon known as blue shift. Conversely, when gas moves away from us, the light waves are stretched out, shifting them toward the red end, which is called redshift. By meticulously measuring these subtle shifts in the spectral lines of elements like hydrogen, oxygen, and nitrogen, scientists can calculate the velocity of the gas along our line of sight. The results paint a vivid picture of an object in dramatic motion. The bright inner disk of the Helix Nebula is expanding outward at speeds reaching several tens of kilometers per second, which is a testament to the violence of the initial ejection from the dying star. To put that into perspective, that is tens of thousands of times faster than a commercial jet airplane. This is not a gentle drift. It is a powerful, ongoing eruption. Furthermore, the expansion is not perfectly uniform. Different parts of the nebula are moving at slightly different velocities, which helps explain its complex structure. The faint outer halo, which was ejected earlier in the star's death process, is expanding more slowly than the inner disk, telling us that the star's mass loss occurred in distinct phases with varying intensity. This velocity information is not just about understanding the present. It is a key that unlocks the past. By combining the measured expansion speed with the nebula's apparent angular size on the sky, astronomers can perform a neat trick to estimate its distance. This method, known as the expansion parallax, works by figuring out how long it would take for the gas, moving at its known speed, to reach its current size. If you know how fast something is expanding and how big it appears, you can calculate how far away it is. This provides a crucial independent check on other distance measurement techniques, and for an object like the helix, which is a cornerstone for understanding stellar evolution. Pinning down its exact distance is incredibly important. These kinematic measurements allow us to rewind the cosmic clock. By tracing the paths of the expanding gas backwards, scientists can estimate when the initial ejection occurred, placing the age of the nebula at around 10,000 years or so. This turns a single dot, beautiful snapshot, into a movie of the star's final moments. We can visualize the star pulsating and shedding its outer layers in a series of eruptions, with the faster-moving inner material eventually catching up to and interacting with the slower, earlier ejecta. This interaction can create shock fronts and compress the gas, contributing to the formation of structures like the cometary knots. Studying these velocities also helps us understand the balance of forces at work. The initial thermal pressure from the star's outburst launched the gas. But now, the continued expansion is largely coasting, governed by the inertia of that initial push against the minimal resistance of the near vacuum of interstellar space. The different velocities between the inner and outer regions also provide clues about the progenitor star itself. The speed of the ejection is related to the gravitational pull of the star and the energy of the outburst. So by analysing the velocity structure, astronomers can infer properties of the star that is now gone, such as its mass and the strength of its stellar winds during its final phases. This is like forensic science on a cosmic scale. For observers, it is a mind-bending concept to grasp that this seemingly static and eternal object is actually a rapidly changing and evolving structure, even if that change is imperceptible over a human lifetime. The entire nebula is growing larger by millions of kilometers every day, but from our distant vantage point, this motion is only detectable through the precise tools of spectroscopy. This measurement of motion is not limited to the main body of the nebula. Even the cometary knots have their own velocity structure, with their tails streaming away from the central star, providing insights into the photoevaporation process that is slowly destroying them. The ability to measure these speeds is a triumph of modern astrophysics, relying on sophisticated instruments on large telescopes that can disperse light into its component colours with extreme precision. It transforms our understanding from a purely morphological one, what the nebula looks like, to a dynamical one, how the nebula behaves and evolves. This kinetic energy is a fundamental part of the nebula's legacy. As it expands, it transfers energy and momentum to the surrounding interstellar medium, helping to stir and mix the galactic gas. So, when you look at an image of the Helix Nebula, remember that you are not looking at a fossil. You are looking at a slow-motion explosion, a continuing event whose dynamics we can precisely quantify. This understanding of its velocity and expansion is the final piece that connects the nebula's violent birth, its beautiful and complex present structure, and its eventual dissolution into the galaxy, where its material, including those precious organic molecules, will travel for eons until it becomes part of something new. It is a reminder that the cosmos is not a static museum display, but a vibrant, moving, and ever-changing system. And through the science of spectroscopy, we can read the velocity of that change written in the very light that reaches us. Seeing the Helix Nebula in motion, expanding and evolving, naturally makes you curious about how it stacks up against other similar objects, because placing it in the broader context of planetary nebulae reveals an incredible diversity of stellar deaths and helps us understand why the helix looks the way it does. If you look at other famous planetary nebulae, you immediately notice they are not all identical twin eyes staring back at us. They come in a spectacular variety of shapes and structures, each telling a different story about its progenitor star and the conditions of its death. For instance, the Ring Nebula, another classic example, appears as a nearly perfect, smooth smoke ring, much more symmetrical and homogeneous than the complex, knotty helix. Then you have extremes like the Butterfly Nebula, which displays incredibly pronounced bipolar lobes, looking like a magnificent cosmic hourglass with wings, a stark contrast to the helix's more subtle elongation. Another fascinating example is the Cat's Eye Nebula, which is incredibly complex with concentric shells, jets, and knots, suggesting a much more chaotic and episodic history of mass loss. So why do these differences exist? The variations are largely dictated by the initial mass of the star, its rotation, the presence of a binary companion, and the strength of its magnetic fields. A star like the one that created the Helix, which was probably very similar to our Sun, tends to produce a more rounded nebula, but the presence of those cometary knots and its slight bipolarity hint that even Sun-like stars can have complex departures. In contrast, the dramatic bipolar shape of the Butterfly Nebula strongly suggests the influence of a binary companion star, whose gravity can funnel the ejected material into two opposing jets, or a very strong magnetic field channeling the outflow. The Ring Nebula might represent a case where we are looking almost directly down the pole of a bipolar structure, making it appear circular, or it could be from a star that shed its layers in a more spherical and steady wind. When we compare their chemical compositions, we also find interesting trends. The helix shows certain abundances of elements like oxygen and nitrogen, which are typical for a star of its initial mass. Comparing this to the chemical fingerprints of other nebulae allows astronomers to trace how different elements are produced and dispersed by stars of varying masses. This comparative approach is like building a classification system for stellar deaths. By grouping nebulae by their shapes and compositions, we can identify the underlying physical parameters that control their final appearance. For example, the presence of complex structures like jets and ANSI, which are symmetric blobs of gas, often points to a high-speed wind that emerged later and interacted with the earlier, slower ejector. The helix has a relatively simple structure compared to some of these more intricate objects, which might indicate a less violent or more orderly ejection process. The size and mass of the nebula are also key comparison points. The helix is one of the largest and closest, which is why we can study it in such detail. But other nebulae might be more massive, indicating a more massive progenitor star. The age of the nebula is another differentiating factor. Some are younger, like the Stingray Nebula, which is only about 2,000 years old, while others are older and more diffuse. By studying this entire population, astronomers can piece together the evolutionary sequence, understanding how a nebula changes from its initial ejection to its final dissipation. The helix sits in a middle ground, old enough to have developed its complex knotty structures, but young enough to still be brightly illuminated. The study of these objects is also crucial for understanding the chemical evolution of galaxies. Each planetary nebula contributes a different mix of enriched material to the interstellar medium, depending on the mass and type of its central star. By comparing the helix to others, we get a clearer picture of the total chemical budget that dying stars provide for the next generation of stars and planets. This comparative method also helps resolve mysteries about individual objects. If we see a feature in the helix that is rare in other nebulae, like its abundance of cometary knots, it forces us to ask what was special about its formation conditions. Perhaps the star had a particular mass loss history, or the surrounding interstellar medium is just right for their formation. Furthermore, advancements in technology allow us to make these comparisons across the electromagnetic spectrum, revealing hidden differences. What looks like a simple ring in visible light might show a complex bipolar structure in infrared or radio wavelengths. This multi-wavelength comparative anatomy is essential for a complete understanding. So, while the Helix Nebula is a magnificent and iconic object in its own right, its true scientific value is amplified when we see it as one data point in a vast and varied family. It represents one common pathway for a sun-like star, but the universe has many other ways for stars to end their lives, each leaving behind a unique and beautiful tombstone. This diversity not only adds to the aesthetic wonder of the cosmos, but also provides the rich data needed to test and refine our models of stellar evolution. By understanding why the helix is different from the butterfly or the ring, we learn more about the physics of mass loss, the role of binary stars, and the intricate dance between a star and its environment during its final, dramatic act. This broader perspective ensures that we appreciate the helix not just for its own beauty, but for the vital role it plays in helping us decipher the entire life cycle of stars throughout the galaxy. After comparing the helix to its celestial cousins and understanding its place in the grand scheme of stellar evolution, it is thrilling to push our imagination further and envision what it would be like to actually travel there, to turn this object of study into a destination for a grand interstellar expedition. Let us craft a narrative, a thought experiment rooted in science, about a hypothetical mission to the Helix Nebula. The journey begins with a spacecraft, a vessel of human ingenuity, launching from Earth and heading towards the constellation Aquarius. The distance is immense, 650 light-years, a span so vast that even with hypothetical future propulsion systems like fusion drives or light sails, the voyage would take centuries. This immediately introduces the first great challenge of such an endeavour, the sheer timescale involved. The crew would not be the same people who left Earth. This would likely be a generational ship, where multiple generations are born, live, and die during the transit. Or perhaps the travellers are in a state of cryogenic suspension, their biological processes halted until the ship nears its target. As the ship cruises through the void at a significant fraction of light speed, the view outside would change slowly. The stars would gradually shift positions, but the destination would remain a faint, unresolved smudge for most of the journey. After hundreds of years of travel, the moment of approach would finally arrive. The Helix Nebula would begin to grow in the forward viewports, transforming from a point of light into a vast, luminous structure. As the ship draws nearer, the nebula would eventually span a large portion of the sky, its apparent size becoming greater than that of the full moon seen from Earth. This visual spectacle would be both awe-inspiring and humbling, a glowing cloud of gas with a dark central region that truly earns its nickname, the Eye of God, staring back at the explorers. The primary scientific objective upon arrival would be to study the nebula's intricate structure up close. The ship would carefully navigate towards the inner disk, but the path would be fraught with peril. The first major hazards would be the cometary knots, those thousands of dense globules, each roughly the size of our solar system. Navigating through this field would be like piloting through a cosmic minefield. Each knot is a world in itself, a shield of molecular gas and dust protecting a colder core from the intense radiation. The ship's sensors would map their complex shapes, analysing the long, glowing tails that stream away from the central star, formed by the relentless photoevaporation. Getting too close to a knot could be dangerous due to potential debris and the turbulent gas flows around them. The mission would deploy probes to sample the material from these knots, seeking to understand their composition, including the complex organic molecules and perhaps even the fullerenes that have been detected remotely. This direct analysis could reveal secrets about the prebiotic chemistry happening in these shielded environments, providing clues to how the building blocks of life are dispersed throughout the galaxy. Another key target would be the central white dwarf. The ship would need to maintain a safe distance from this stellar remnant, as it is incredibly hot and emits intense ultraviolet radiation. Specialized shielding would be essential to protect the vessel and its crew from this harmful radiation. From a safe vantage point, instruments would study the white dwarf in unprecedented detail, measuring its temperature, analyzing its spectrum to confirm its carbon-oxygen composition, and observing its interaction with the surrounding nebula. This could provide ground truth data to validate models of stellar evolution and white dwarf cooling. The crew would also study the dynamics of the expanding gas itself. They could release sensor drones into the nebula to measure the velocity of different regions, confirming the expansion speeds of tens of kilometers per second that we have measured from Earth. They might even observe shock fronts where faster-moving material collides with slower ejecta, creating ephemeral glows and complex structures. The halo of the nebula, much fainter and more extended, would be another area for exploration, revealing the history of the star's mass loss over thousands of years. The dangers of this environment are not to be underestimated. Beyond the radiation, there is the risk of collision with microscopic dust grains or larger debris moving at high speeds. The nebula is not a static picture. It is a dynamic, expanding shell, and the ship would need to constantly adjust its trajectory to avoid these hazards. The violent history of the place means that the gas is turbulent, and magnetic fields, though weak, could pose additional challenges to navigation and instrumentation. Furthermore, the psychological impact on the crew would be significant. Being so far from home, surrounded by the eerie beauty of a stellar tomb, could evoke profound feelings of isolation and perspective. They are witnessing the end of a star, a fate that awaits our own sun, which might lead to philosophical reflections on the impermanence of solar systems and the resilience of life. Though we must keep the narrative focused on the experiential and scientific aspects, the mission would also have an archaeological component. In a sense, piecing together the history of the progenitor star by analysing the chemical gradients and the distribution of elements in the gas. The crew could reconstruct the sequence of nuclear fusion events that occurred in the star's core, effectively writing its biography. The data collected would be transmitted back to Earth, but with a 650-year delay. The scientists who receive it would be descendants of those who launched the mission, highlighting the long-term commitment of such exploration. This narrative serves a vital purpose. It makes the abstract concepts of astronomy tangible. The Helix Nebula is no longer just data and images. It becomes a place, an environment that can be explored. It bridges the gap between the cold, hard facts of astrophysics and the innate human drive for adventure and discovery. It inspires us to think about the future of space exploration, the technological hurdles we must overcome, and the kind of courage required to send a mission into such a distant and unknown realm. While this is a work of fiction, it is grounded in the real science of the Helix Nebula, and it reminds us that the wonders we see through our telescopes are not just points of light, but potential destinations, waiting for the day when humanity can reach out and touch the cosmos. This story of a journey to the Helix is more than just a tale. It is a projection of our curiosity and our desire to become an interstellar species, to learn not just by looking, but by going. That thrilling vision of an interstellar journey makes you appreciate all the more the incredible images we can capture right here from our own planet. Because those stunning portraits of the Helix Nebula are not simple snapshots, but the product of a meticulous and artistic process known as astrophotography, which allows us to see far beyond the limits of our human vision. The iconic pictures you see online or in books are the result of long exposure photography, a technique where the camera's shutter is left open for a very long time, not for a fraction of a second but for many hours, sometimes spread over several nights. This is necessary because the Helix Nebula is an extremely faint object. Its light is so dim that our eyes, which can only gather light for a brief moment, simply cannot collect enough photons to see any detail or colour. A telescope acts as a giant light bucket, funneling this faint light over a long period onto a digital sensor, slowly building up a detectable image one photon at a time. Modern astrophotographers use sensitive cooled cameras, often called CCD or CMOS cameras, specifically designed for low-light work, which are much more efficient than the human eye or old photographic film. But just collecting light is not enough to truly bring out the scientific and aesthetic details. Photographers use special filters that screw into the camera or telescope. These filters are not like Instagram filters. They are precise optical components that only allow a very specific wavelength of light to pass through. For emission nebulae like the Helix, the most common filters are those that isolate the light from specific ionized elements. A hydrogen alpha filter, for instance, only lets through the deep red light emitted by excited hydrogen atoms. An oxygen 3 filter transmits the greenish-blue light from doubly ionized oxygen. Sometimes a sulfur 2 filter is used for a different red emission line. The photographer will take separate long exposures through each of these filters, creating individual black and white images that map the distribution of each element in the nebula. These individual exposures, or sub-exposures, are then combined and assigned colours in post-processing software. The hydrogen alpha data might be assigned to the red channel, the oxygen 3 to the green and blue channels, creating what is known as a false colour or mapped colour image. While these are not the true colours you would see with your naked eye, they are scientifically informative, revealing the physical structure and chemical composition in a way that is visually intuitive. The term false colour is a bit misleading. A better term is representative colour, as it translates invisible data into a visible spectrum we can understand. After capturing all this data, the real magic happens in the digital darkroom. The raw frames are first calibrated using dark frames, which map the camera's noise, flat frames, which correct for vignetting and dust spots, and bias frames, which remove electronic bias. Then, all the sub-exposures for a given filter are stacked or aligned and averaged together using specialized software. This stacking process dramatically increases the signal-to-noise ratio, smoothing out random noise and bringing out the faint details of the nebula against the background. Once the stacked images for each filter are ready, they are combined into a color composite. This is where the art meets the science. The processor will carefully adjust the levels, curves, and saturation to balance the image, striving to reveal the intricate structures like the filaments and cometry knots without artificially creating them or blowing out the brightest parts. Techniques like deconvolution or sharpening might be used to enhance fine details, but this must be done judiciously to avoid introducing artifacts. The goal is to create a natural-looking image that is both beautiful and a faithful representation of the data for the Helix Nebula. This often means bringing out the delicate radial patterns of the knot's tails and the subtle gradients in the main ring. The final image is a testament to patience, skill, and technology. It represents not a single moment in time, but the cumulative effort of many hours of data acquisition and careful processing. This process allows amateur astronomers with backyard telescopes to produce images that would have been the envy of professional observatories a few decades ago. It democratizes the beauty of the cosmos, enabling anyone with dedication and the right equipment to create their own cosmic masterpieces. So, the next time you see a breathtaking image of the Helix Nebula, remember that you are not just looking at a pretty picture. You are looking at a labour of love and a sophisticated technical achievement. You are seeing the invisible light of specific atoms translated into a visual form, and you are witnessing the cumulative glow of hours of starlight, painstakingly gathered and processed to reveal the hidden beauty of a dying star. This process connects us directly to the cosmos, transforming us from passive observers into active participants in the revelation of the universe's wonders. The incredible astrophotography we just discussed is not just the domain of professionals. In fact, a global community of dedicated amateur astronomers plays a vital and often unsung role in keeping a watchful eye on the Helix Nebula and other celestial wonders, contributing valuable data through their passion and increasingly sophisticated equipment. While large professional telescopes are often oversubscribed and focused on specific, short-term research goals, amateur astronomers can provide a continuous long-term vigil, monitoring objects like the Helix for subtle changes that might otherwise go unnoticed. The equipment available to serious amateurs today is astonishing, with moderate to large aperture telescopes, sensitive cooled cameras, and the same narrowband filters used by professionals. They are capable of capturing high-quality images and scientific data from their backyards or remote observatories. These images are not just for beauty, they can be used for scientific purposes, such as photometry, which is the precise measurement of an object's brightness. Amateurs can monitor the central white dwarf of the Helix for any slight variations in its light output, which could provide clues about its stability, cooling process, or even the presence of a faint accretion disk. Furthermore, by collaborating in organised networks, amateurs can conduct systematic monitoring campaigns, creating a long-term legacy of observations that professionals can use to study the nebula's evolution over decades. This is crucial because professional observatories rarely have the telescope time to monitor a single object year after year. The global nature of the amateur community means that when a professional telescope in Chile loses the Helix to daylight, an amateur in Australia can pick up the watch, providing nearly continuous coverage. This collaborative spirit is facilitated by online platforms and organisations that coordinate observations, share data, and standardise techniques. The contributions go beyond simple imaging. Some amateurs specialise in spectroscopy, using affordable spectrographs attached to their telescopes to analyse the light from the nebula, confirming expansion velocities and chemical compositions, thus providing independent checks on professional data. This democratisation of science is powerful. It allows anyone with dedication and curiosity to participate in genuine astronomical research. The value of this long-term dataset cannot be overstated. While the Helix Nebula changes slowly, on timescales of centuries or millennia, very subtle shifts in brightness or structure might be detectable over a human lifetime with precise and consistent measurements. Amateurs are perfectly positioned to conduct this patient work. They also serve as scouts. If something unusual suddenly happens, like an unexpected brightening, the amateur community is often the first to notice and alert the professional community, who can then turn larger telescopes toward the event. This partnership is a beautiful symbiosis. Professionals develop the theories and have access to the largest instruments, while amateurs provide the sustained, grassroots monitoring that fills in the temporal gaps. For the individual amateur, the reward is the profound satisfaction of knowing that their hobby contributes to our collective understanding of the universe. Capturing a detailed image of the Helix is a technical achievement, but knowing that the data embedded in that image could be used for science elevates the pursuit to another level. It transforms stargazing from a passive activity into an active contribution. This model of pro-am collaboration is becoming increasingly important in astronomy. As the volume of data from sky surveys grows and professional astronomers rely on distributed networks to help analyze and monitor the dynamic sky. The story of the Helix Nebula is therefore not just written by the scientists at major observatories. It is also written by thousands of enthusiasts around the world who dedicate their nights to patiently gathering photons from this distant cosmic eye. They are the guardians of the night sky, maintaining a constant, vigilant presence and ensuring that the subtle stories of objects like the helix are not lost in the passage of time. Their work ensures that our view of the cosmos is not just a series of isolated snapshots, but a continuous, living record, enriched by the passion and perseverance of a global community looking up and wondering. The collective vigil kept by amateur and professional astronomers alike on the Helix Nebula inevitably leads us from the purely scientific to the deeply personal, as this object transcends its physical nature to become a powerful philosophical symbol, inviting us to reflect on existence itself. It is a cosmic Rorschach test, and what we see in its intricate form speaks volumes about our own place in the universe. The most immediate theme it presents is the intimate connection between life and death, specifically that the end of a star can be an event of breathtaking beauty. This challenges our terrestrial notions of death as merely an end or a decay. Here, it is a transformation, a brilliant and colourful dissipation that illuminates the surrounding void. The helix shows us that an ending can be simultaneously tragic and magnificent, a final act that contributes something new and beautiful to the cosmos. This is a lit death, a phrase that captures the paradox of a destructive process that generates immense light and structure. This leads directly to the concept of cosmic recycling, a notion that is both scientifically accurate and spiritually resonant. The nebula is not just a tomb, it is a dispersal mechanism for the very elements that make up our world and our bodies. The carbon, oxygen, and nitrogen atoms that were forged in the heart of that star and then expelled in its death throes are the same atoms that form the foundation of life on Earth. We are, quite literally, made from stardust, and the Helix Nebula is a vivid, nearby illustration of that process. It physically connects us to the cosmic cycle of birth and death, making our own existence a part of this grand, ongoing narrative. This realization can be both humbling and empowering. It forces a perspective on scale that is difficult to grasp. The Helix Nebula is 650 light-years away and measures about 3 light-years across, a scale that dwarfs human comprehension. Our entire recorded history, all our triumphs and tragedies, have occurred on a tiny planet orbiting an average star, a mere speck in comparison to this expanding cloud of gas. This can make human endeavours seem insignificant, a fleeting moment in the cosmic drama. Yet, there is a counterpoint to this insignificance. We are the part of the universe that has become self-aware. We are the means by which the cosmos can observe and contemplate itself. The image of the eye of God is particularly potent here. It can be reinterpreted not as a deity watching us, but as the universe opening its eye, with our own consciousness as the pupil through which it perceives its own grandeur. We are the universe understanding its own laws, unravelling its own history, and marvelling at its own beauty. This gives human life and intellect a profound purpose within the vast, impersonal expanse of space and time. The nebula also speaks to the inevitability of change. It is a dynamic object, not a static monument. It is expanding, fading, and transforming, just as everything in the universe is in a state of flux. This mirrors the human condition, where nothing remains the same. The helix reminds us that change is the fundamental law of existence. From the smallest cell to the largest galaxy, its story, from stable star to red giant to planetary nebula to white dwarf, is a story of constant, inevitable transformation. This can be a comforting thought when facing personal or global upheaval. Change is not an anomaly, but the natural order of things. Furthermore, the nebula symbolizes the interconnectedness of all things. The death of this one star enriches the galactic environment, providing the raw materials for future stars, planets, and potentially new life. Our solar system, and we ourselves, are products of such ancient stellar deaths. This creates a tangible link across space and time, connecting us to events that occurred long before our sun was born. We are not isolated observers, but active participants in a vast cosmic ecology. The Helix Nebula, therefore, is more than an astronomical object. It is a mirror. It reflects our questions about mortality, purpose, and our place in the grand scheme. It offers no easy answers, but provides a canvas upon which we can project our deepest thoughts and feelings. It tells us that endings are not full stops, but semicolons, that beauty can emerge from destruction, and that we are both infinitesimally small and immeasurably significant. It is a symbol that merges the scientific and the spiritual, reminding us that the quest for knowledge about the external universe is ultimately a quest to understand ourselves. In its glowing gases and dark central void, we see the story of all things, a story of change, of recycling, of beauty born from catastrophe, and of a universe slowly, gradually, becoming aware of its own astonishing existence through us.